First of all, I'd like to thank the organizers for putting together this one-for-one conference and program, and for giving me the opportunity to present our work here. Today, I'm going to talk about backfiring bosonization, and this talk is based on the paper we put out last year in collaboration with a fantastic collaborator, Philip Smith, who is currently in CISA. And today, so what's the goal of this talk? So the goal of this talk is to explain a small puzzle about bosonization in 1+1D. So in order to explain the puzzle, I'm first going to review bosonization map in 1+1D just to set up the stage. And then I'm going to explain the puzzle using a very simple example. And I'm going to present a way to solve the puzzle. And then I'm finally going to summarize and provide some future directions. Okay, so let me start with the basic stuff. So what is a fermionic quantum field theory? Well, one way to define fermionic quantum field theory is that it's a fermionic quantum field theory with fermion parity symmetry, -1 to the f. And this fermion parity symmetry acts on the fermion by giving fermion a minus sign. And because it's a symmetry, we can turn it into background field. This background field is just a Z2 gauge field, a flat Z2 gauge field. There is a closely related definition, but not quite equivalent, is that the fermionic quantum field theory is the quantum field theory equipped with a spin structure. So what is spin structure? Roughly speaking, spin structure specifies the boundary condition of the fermions. So if the fermion goes around the cycle of the space-time manifold and it gets a minus, then it's the NS spin structure, and otherwise it's the R spin structure. The spin structure, mathematical spin structure, is a torsor over the Z2 gauge field, which means that if you start with spin structure, if you shift the spin structure with a Z2 gauge field, you will get another spin structure. Okay, and so the first definition is mostly common for condensed matter physics, I think, but the second definition is more common, perhaps in high energy physics community. Yes.
I'm confused by the first definition.
Yeah.
So how do you abstractly say this is a fermion parity symmetry? I thought to make it precise, you have to say that -1 to the f shift the coupling to the spin structure.
That's the point of the next slide.
Okay. Yeah, but so far it's not complete.
Yeah. So far. Yeah. Okay. So I'm just trying to give you like two separate.
Because so far you cannot tell the difference between this and an ordinary Z2.
Yes,
okay. Good. Thank you.
And so this conference is like an interplay between different communities, so I think it better combine them and say that the fermionic quantum field theory is a quantum field theory equipped with both the spin structure and the fermion parity symmetry. And if you couple to the background field for both of them, then their background fields are not completely independent, so they depend on the combination.
I just have a question, maybe related to the last question.
Yeah.
I mean, can you just say that you have gauge invariant fermion operators, and those are the ones which are charged under the Z2?
Yes.
So why you don't need to mention spin structure at all? You can just mention this -1 to the f, but you have to specify what I just said.
Yeah. But so the whole point
complete.
of the talk is to try to see the difference between them, and you will see that there is some situation where you are enforced to consider the difference between them.
Okay.
So we have a partition function of the fermionic theory. I turn on the background field, so I turn on the spin structure and the background field for the fermion parity. And not every configuration of rho and A are independent. And in particular, it's natural to say that the partition function depends only on their linear combination, rho plus A. And so later I'm going to suppress this 0 just for simplicity. Okay. Now, let's review what's the bosonization. So bosonization in history can mean many things. And here I'm going to highlight two different notions of bosonization. One is what is usually called the boson-fermion duality, which means that you have a given theory, and you can write this theory in terms of two different degrees of freedom. One is the bosonic degree of freedom, and the other is the fermionic degree of freedom, possibly coupled to some gauge fields. So this is called boson-fermion duality, and it has a long history. And depending on like which dimension you are in, sometimes it can be, it's an exact duality, and sometimes it's an emergent IR duality. The second notion of the bosonization is the bosonization map, which is an operation that maps the fermionic theory to a different bosonic theory. So I have to highlight that these two theories are really different. They are not the different description of the same theory. So these two theories are really different. And on the lattice, this is often called the Jordan-Wigner transformation. And in recent years, there has been a lot of like updated discussion about the bosonization map. Sure.
Maybe I'm wrong, but I always thought that the second viewpoint is just like a refinement of the first point, in the sense that when you write the fermionic theory in terms of bosonic degrees of freedom, if you have gauge invariant fermions, obviously you are losing something, so you have to gauge some symmetry to have an exact.
They are closely related, but they are not exactly equivalent. First, for example, the second one, you can implement it on arbitrary fermionic theory. But for the first one, there are only a couple of known examples. So that's, yeah.
Sorry, if I take the second one and I gauge fermion parity, does not give me the first one?
So if you start with a fermionic theory and modulo some caveats, which are discussed later, then you can always gauge that, and you will get a different theory.
Which is not the first one.
Whether that theory can be written in a nice Lagrangian, has a nice Lagrangian description in terms of purely bosonic degree of freedom, that's not always the case, right? Okay. So in this talk, I'm going to mainly...
One more question in this direction. You know, if I'm thinking in terms of, say, supersymmetric examples, then in 1+1, you can present all of them as fermionic, right? Like for fermionic interaction, it works there. However, there's a number of sectors in fermions it's like kind of non-invertible in the sense that the number of sectors which are not used. So this relation between, say, fermion-boson presentation and pure fermionic presentation is not, it contains some number of extra fermions which are not enter this classification. I'm not sure whether it's related to what you're doing, but there it's clear that this sector of a fermion and only part of the sector is related to normal boson fermion presentation.
Yeah. I'm not quite familiar with the supersymmetric setup. So, I think Shu can maybe clarify a little bit.
Yeah. So I think that's the usual point of view. So taking that, you know, in the fermionic supersymmetric CFT, you have Raman sector, you have Neveu-Schwarz sector. But when you go to the bosonic description, only certain subsector of them appear. But in my mind, that's right. But that's actually not a complete picture. In the bosonic CFT, you can also look at some twisted sector state with respect to some ordinary Z2. If you include those, then the number of sectors on the bosonic side will be equal to the number of sectors on the fermionic side. It's just that in the literature, usually people don't discuss the twisted sector of the bosonic side. Yeah, but in some of the more recent papers, this has been discussed quite extensively. Yeah.
Okay. So today, I'm mainly going to use the second notion. So when I say bosonization, I always mean bosonization map. So I'm going to define what do I mean by bosonization map more concretely. So one way to define the bosonization map is to sum over the fermion parity. So you have a partition function. You can couple to a spin structure and the fermion parity gauge field. And I promote this, which is originally capital A background field, to be a dynamical field and sum over the spin structure, or sum over the fermion parity gauge field. So using the equality between this description and this description, namely that the partition function only depends on the linear combination between them, then I can write the sum as in this way. And you can check that so after summation, the whole thing is independent of the choice of the spin structure. So it's a bosonic theory. So, And then, alternatively, you can also define the bosonization map to be a sum of the spin structure. So how do we sum of a spin structure? Well, we can decompose spin structure into some reference spin structure and some Z2 gauge field, using the property that the spin structure is a torsor of the Z2 gauge field. And then I'm again going to use the relation, the relation that the Partition function only depends on the summation of them. And then after changing of the variables of this little a by shifting little a by capital A, then I'm getting the same expression, which is again the bosonic theory. So this simple, almost a trivial computation tells us that the bosonization can either be interpreted as the sum over the fermion parity or sum over the spin structure. They are equivalent. Okay. And then, as we all know, that just as gauging ordinary Z2 symmetry, after summing over the fermion parity gauge field, there is a bonus or quantum Z2 symmetry in the resulting series, so which is the bosonic theory. So we can try to turn on the background field for this bonus Z2 symmetry. So let's call the background field to be capital B. So we turn on this background field in this particular way. But you can check that on the right-hand side, the theory is not manifestly invariant under the shift of the spin structure. Because you shift the rho by some arbitrary number, then you can check that this is not invariant, because you can redefine the A, and the shift of the A will influence the first term. But this problem can be cured by adding another counter term, which depends on only the background field and the spin structure. So which means that after turning on the background field for the Z2 symmetry in the bosonic theory, the theory is bosonic only in disguise. So we need a counter term to make sure that the resulting theory is invariant under the shift of the spin structure. Okay, so now we have a fermionic theory with a fermion parity symmetry of spin structure, and we have bosonic theory with the bonus Z2 symmetry. Now we can use this symmetry to decompose the Hilbert space. For example, let's consider a torus space-time, decompose the Hilbert space into 4 different sectors. So we decompose the fermionic theory into these 4 different sectors. These 2 label the boundary condition in the space direction, and these 2 labels whether the Hilbert space is even or odd under fermion parity transformation. And similarly, for the bosonic theory, we can again use the Z2 symmetry to decompose the Hilbert space into 4 sectors. And what bosonization does, so here we have a definition. So we have a very concrete formula for the bosonization map. And we can try to implement this map on the torus. And if you do so, then you will find that what bosonization map does is to keep the first sector to be invariant, but rotate the remaining 3 sectors clockwise. Okay, so let's try to test this using an example. So suppose that we start with a fermionic series, which is the 1 Marginal fermion. And then the partition function, you can work out the partition function of these 4 sectors. And indeed, the 4 partition function, which is the sum of the S and the T, indeed contains half integer states. So it means that the theory is indeed a fermionic. And after bosonization, I'm just using this map that the bosonization rotates these 3 sectors. Then after this map, the partition function is the S plus U. And indeed, both S and U only contains the states with integer spin, so they are bosonic. So this is the famous Ising CFT. Now let's consider another more subtle example, which is where the fermion theory is the 8 Marginal well fermion. And then you can again work out the partition function in these 4 sectors. But famously, due to the triality of the spin SO8 algebra, the algebra, then these 3 different sectors have the same partition function, and both contain the fermionic states. So it means, and then if you use our bosonization map, you find that if you start with the fermion theory, whose partition function is S plus T, which contains the fermion states, and then after bosonization map, it becomes S plus U, which again contains the fermionic states. So it means that after bosonization, you get some fermionic theory again. So which is very confusing when we encounter this example. So the puzzle is that after presentation, the theory is still fermionic. Okay. So let me abstract the puzzle. So using this diagram. So a good bosonization is the bosonization which maps the fermionic theory to a bosonic theory. But here we found an example where if you start with a fermionic theory, you do the bosonization, you get a fermion theory back again. So this is what we call the backfiring bosonization.
So fermionic theory means what for you? What's your definition?
So fermionic theory means, so in this torus setup, it means that the partition function counts the states, and the state including this half integer spin state.
Right, but isn't that just the endpoint of a Z2 line defect?
So this is the untwisted sector. So I'm considering the NS sector and consider the untwisted sector. So I'm not considering the twisted sector here.
Okay. Yeah. Okay, thank you.
Yeah. So this is the puzzle. And here, to clarify a little bit, backfiring means to have the reverse of the desired or expected effect. So it means that the bosonization is supposed to do this job, but it doesn't do its job, so it's called a backfiring bosonization. Okay, so this is the puzzle. So next, let me present a solution, our solution to this puzzle. Yeah.
But you still get the dual symmetry, right?
I still get a dual symmetry, right?
But is that symmetry again -1 to the f, or is another symmetry?
It's a Z2 symmetry, and that will act on the fermions by a minus sign. Yeah.
So it's again -1 to the f. So you're gauging -1 to the f, but
And
you have -1
against
against the gain.
Yeah.
Is this a property only of -1 to the f, or can happen also for normal Z2
later
symmetry?
I'm going to give you an explanation.
Okay.
Okay, so how to understand this very confusing situation? The key to understand this puzzle is to understand the gravitational anomaly in 1+1D theory. So let me first discuss a little bit about this gravitational anomaly. So gravitational anomaly in 1+1D theory is described by the gravitational transcending term, and it's labeled by an integer. And just as, so by the way, this integer is related to the Carl-Sagan charge in this simple way. And just as how we usually define the transcending term, we usually promote it to a 4-dimensional integral. So here we do the same. So suppose now let's consider this anomaly in full action, and suppose that we assume that this M3 is a closed manifold for the moment. So there's no 2-dimensional boundary. Then how do we define this term? So we define this term to be the 4-dimensional integral. We just lift it to the bulk. And we demand that the theory, the thing you get is independent of the choice of the 4 manifold. Okay, so more concretely, so you take the two different extensions, M4 and M4 prime, and try to compare them. And once you compare them, you're going to find that their difference is given by this expression, which is given by the signature of this closed 4 manifold. Okay. And you demand it, we want to demand that this thing must be identity. Now, the signature has a property that it must be it's an integer on a generic 4 manifold, but the 16 times the integer on a spin manifold. So it means that when n is a multiple of 16, this guy is always identity, so it's always satisfied. Therefore, we don't have to extend the spin structure of the 3-dimensional theory to the 4-dimensional manifold. Therefore, the 3-dimensional theory is independent of the spin structure. On the other hand, when n is not a multiple of 16, then you have to demand that this sigma is a spin manifold so that this guy is trivial. So it means that you have to extend the spin structure into the 4-dimensional bulk, which means that 3-dimensional theory depends on the spin structure. So the upshot of this discussion is that when n is not a 0 mod 16, then the 3-dimensional gravitational transcending term depends on the spin structure. which means that spin structure is anomalous in 1+1D. When the gravitational anomaly is is 0 mod 16, then the gravitational Chern-Simons term is independent of the spin structure, and the spin structure is free from anomaly in 1+1D in this particular case. So, to summarize a little bit, it means that the Z-valued gravitational anomaly in 1+1D induces a Z16 valued anomaly of the spin structure, which depends on the gravitational anomaly mod 16. Mathematically, you can also understand the previous discussion in this simple way. So the gravitational anomaly for the bosonic theory is classified by a 16 times integer, and the gravitational anomaly for the fermionic theory is classified by an integer. So if you want to remove the diffeomorphism part and just focus on the anomaly for the spin structure, then you just take the quotient between them and you'll get a Z16 value the same. Okay. So this observation has a direct consequence. So the consequence is when the gravitational anomaly is not 0 mod 16, then we cannot sum over the spin structure because to get a well-defined theory. So if you literally sum over the spin structure, you'll get something ill-defined as a bosonic theory. And this is indeed the case. For example, in our first example, we have the one-minor fermion whose gravitational anomaly is 0. And so therefore it's safe to sum over the spin structure. You'll get a well-defined bosonic theory, which is the Ising CFT. But in our second example, we have the A-minor well fermion, and it has the gravitational anomaly A, which is not 0 mod 16. Therefore, summing over the spin structure does not give you a healthy bosonic theory. Okay. So this partially solves our puzzle, that the reason that we get this situation is that there is an anomaly for the spin structure, and we bosonize in the presence of the anomaly of the spin structure, which means that something has to go wrong. Okay. But this is not quite the end of the story. I haven't told you that why in this case, in the case when the gravitational anomaly is 8 mod 16, the bosonization will map the fermionic theory back to a fermionic theory. You may wonder that it can give you something more ill-defined. Another puzzle, which if you remember that in the beginning of the talk, I presented this simple derivation that if you so you can interpret the bosonization as in these two equivalent ways, and the end result is the bosonic theory. So what goes wrong with that? So the key to understand what goes wrong in this simple computation is that this identity does not hold in the presence of the anomaly for the spin structure. So why? Because when the gravitational anomaly is 8 mod 16, then the left-hand side of this equation lives at the boundary of this gravitational Chern-Simons term, which depends on the choice of the spin structure. And the spin structure here is low. Note that here in the bulk, it does not depend on the choice of A, because A, which is a Z2 gauge field, does not suffer from the anomaly for this particular case. On the other hand, if you look at the right-hand side of this equation, this partition function lives at the boundary of the gravitational Chern-Simons term, but it depends on another spin structure where the spin structure is shifted. So you cannot identify these two partition functions, which are the states in these two invertible series, because they live on the boundary of two different invertible series, because in the bulk the gauge field are different. So you cannot identify them. But what you can do is to consider a square of them. If you consider a square of them, the 2 copy of the theory is free from the anomaly of the spin structure. Therefore, you can identify them. The bulk are independent. So remember, so if you take the square of them, the bulk, so the total gravitational anomaly is 0 mod 16. Therefore, the bulk is independent of the spin structure. Therefore, you can compare the two states. You can compare the partition function which live on the boundary of the same three-dimensional box theory. So therefore, there's a canonical choice to identify them. Now, here we have an equality for the square of the partition function, but if you take the square root, then there must be an ambiguity, and ambiguity must be a sign. So this is the best we can say, that we can relate these two partition functions, but they are almost equivalent, but they are equivalent up to a sign ambiguity. Okay. So now let's revisit the calculation we did in the beginning. Yeah.
I have a small confusion. So usually, when we try to gauge a symmetry that is anomalous, we get like a zero partition function. We just say the theory becomes inconsistent. So now you're saying that you're gauging it, the theory doesn't become inconsistent, but goes back to itself. So
yeah, so it will not be a consistent bosonic theory. But yeah, because we are considering a very weak anomaly for the spin structure, which is only the mod 2 part. So in this case, you will not get a consistent bosonic theory, but you will get a consistent fermionic theory. And I'm going to explain in the next slide. Yes.
I also have a clarification question. I thought we only need the bulk Chern-Simons term if the boundary has a chiral central charge. Why do you have a bulk Chern-Simons term for the gravitational?
The boundary indeed has a chiral central charge.
Oh, you're considering a chiral 1+1D theory?
Yeah. So it has a non-trivial gravitational anomaly.
Oh, okay, you're restricting to that case. Okay, I thought you had examples where
by chiral, let me clarify. So by chiral, all what I mean is that the CRL and the CR are not equal.
Yeah, exactly.
But not just like, sometimes when people say chiral, it means that the CR is 0.
Right.
Just have CR.
So this whole backfiring story is specific to these kinds of theories?
That's right.
Okay.
That's right. Okay, so let's try to revisit the calculation in the beginning. So again, we restricted to a case when the gravitational anomaly is 8 mod 16. Then, on one hand, we can gauge the fermion parity because A is nothing but a Z2 gauge field, so we can just sum it over. There's no anomaly for this Z2 gauge field. And the result we get will explicitly depend on the choice of the spin structure. So this is why we get a fermionic theory. On the other hand, so by the way, so because there's a sign ambiguity, so we cannot use this equality to make progress. So we just stay with this prescription where we couple the theory from fermionic theory to spin structure and the Z2 gauge field separately. So on the other hand, we cannot sum over the spin structure because you know that for different choice of the spin structure, there is a sign ambiguity between them, and therefore, if you sum them over with a relative sign ambiguity, the whole summation will be ambiguous, and it does not quite make sense to talk about the summation. Okay, so this is the result. So to summarize a little bit, it means that we see that in the presence of the gravitational anomaly, which is 8 mod 16. The sum of the spin structure and the sum of the fermion parity, they are no longer equal. They bifurcate. And so the situation can be summarized in this table. So when the gravitational anomaly is 0 mod 16, so there's no anomaly for the spin structure, and you can either do the gauge for fermion parity and the sum of spin structure, and they give you the same results as what we did in the beginning of the talk. When the gravitational anomaly is 8 mod 16, then I claim, we see that we can still gauge the fermion parity. You will get your fermionic theory, but it does not make sense to sum over the spin structure. So you can only do one of them. I haven't explained what happens when the gravitational anomaly is of other values, but it's not hard to believe that in both cases, in this case, you cannot gauge the fermion parity and sum of the spin structure. It will give you the zero partition function in general, as Andrea said. Okay, so this is the summary. So in one sentence, the bosonization in the presence of the gravitational anomaly is very subtle because the gravitational anomaly will induce the anomaly for the spin structure and it will obstruct you from doing the bosonization. So here are a few future directions that I want to discuss. So first of all, as we see that so if the theory is invariant under the backfiring bosonization, which maps one fermion theory to a fermion theory, then there's some special situation where the two fermion theories are equal. So it means that it defines, so backfiring bosonization becomes a symmetry of the fermionic theory, and it's a non-invertible duality symmetry, turns out. And the question is whether we can say something interesting about it. Second future direction I want to discuss is the generalization to higher dimensions. So if you crank up a dimension, so if you go up the dimension by 1, then you will see that there's no backfiring bosonization problem, but there are also many other interesting things to explore. For example, in that case, there are 16 ways to do the fermion bosonization, as one of the paper by Zheng and Poshen discussed. Then you can also discuss what happens if you do the bosonization in the presence of the other symmetries. Just as gauging, you may know that if there is a mixed anomaly, then if you gauge the subgroup, then there is a new symmetry in the resulting theory. And same for the bosonization. So this is also something interesting to explore. Yeah, so that's what I have. I'll stop here. Thank you very much.
Thanks for the nice talk. So can you go to the previous slide? Okay. So you're saying that when n is 8 mod 16, can you explain why it makes sense to gauge fermion parity in general, and why it's a fermionic theory? You explained it in one example of 8 chiral fermion, but why that's always true?
So if you couple the theory to the background field for example, for the fermion, so for the Z2 gauge field and the spin structure, then you ask what is the obstruction to sum over this A in the presence of the fermion parity.
But why is it even consistent? Why you could consist, because when there is an anomaly, sometimes it's even inconsistent to couple it to background gauge field.
Why? Like
because there could be a minus sign.
Yeah. If there's okay, so I haven't explained that. So now you can check that under the gauge transformation of this little a, the partition function, whether the partition function is invariant or not. And the claim is that it is invariant. And the reason that it's invariant is because the anomaly for this Z2 gauge field in the presence of the spin structure is classified by the Bordisson group omega-3 spin BZ2, which is the ZA value. And this theory, because the gravitational anomaly is A mod 16, so it's a copy of the minimal theory, so this ZA anomaly must vanish. So in this case, we can gauge we can gauge this Z2 gauge field without obstruction.
I see. So as a Z2 symmetry is anomaly free, it's only.
Yeah, that's right. And that's another. So relatedly, that's why I claim that in the bulk theory is independent of the Z2 gauge field.
I see. Yeah. One related question is that you show the partition function for 8 chiral fermion on a torus.
Yes.
How about higher? Is there any subtlety in higher genus surfaces?
Yes, the claim. So if you buy this argument, by this general statement, then it will tell you that for arbitrary genus, the theory is again fermionic. So, but I haven't do the computation yet. Yes.
Did I understand right that your calculation is for the untwisted sector? So what happens in the twisted sectors?
So what happens in the twisted sector? Let me see. So the twisted sector are in these two sectors. So these two sectors, and you can see the partition function in these two sectors. So for this non-anomalous case, for example, in the Ising CFT, there is indeed a fermion theory in the twisted sector. But for the other example, both twisted sectors are contains the fermion as well.
So it's also not consistent, you say?
Yeah. So when we say that the theory is bosonic fermionic, we only consider the states in the untwisted sector, right? So, yeah, it's the Pachin function. This is what the untwisted sector Pachin function computes. Just trace over.
Thanks for a nice talk. Can you go to, I think you have the slides that shows some ambiguity if you shift the spin structure by some gauge fields, right? For n equals to A. You have some sign ambiguity. I want to ask whether you know how that sign ambiguity depends on spin structures and A.
Yeah, it's complicated. So.
Oh, I see, but it's written.
But it will depend on the spin rho and A.
I see. And then the second question is, in higher dimension, there's also, for example, U structures or other structures.
Yeah, so the closest analog of the story here is the 5+1 dimensional theory, which suffer from the gravitational anomaly, and you can still discuss this. And if you go to lower dimension, then there's no subtlety here. No backfiring bosonization.
And does it work out in 6 dimensions?
I think Philip has some computation, but yeah, I haven't.
I see. Yeah, thanks.
Maybe while you're running, I can ask my question. What is the fusion of backfiring bosonization with itself? Because you're saying it's a non-invertible symmetry if it goes back to the same theory.
Yeah, I don't have that on top of my mind, but I think it's just like the Ising fusion case. Yeah, Ising fusion. Trialogy. So that's right. Yeah. So then what's the fusion? Oh, I know. Yeah, okay. Yeah. But okay.
Okay, I'm trying to go from a little bit different side. If you can, some number of years ago, together with Schiffman, we considered, say, it's a subsymmetric extension, say, in 1+1, let's say, Simon-Gordon model.
Yes.
Adding fermions there. Okay, later on, it was Witten also was considered similar example. But when you add in this fermion, the series clearly says the fermionic symmetry in explicit form. However, once you go into king sector, which in this theory, then you will find out that that the king breaks the two symmetry. It's neither fermion nor boson. It's like a linear combination of fermion and boson in this case. And it's not like your anomaly is something different, right? Because it's similar to like a fractional charge, because it's associated with something sitting at the boundary.
But I believe that in that case, there's no subtle anomaly issue because the model you mentioned, I think, has 0 central charge. It's like non-chiral theory. Is that right? Because you are referring to this.
Probably it's not a chiral theory. I agree, but this Z2 is broken, in this sense, on the king, because it's, as I said, it's like analog of
you mean the
fractional charge.
Yeah. So in the twisted sector, the theory is the states in the twisted sector is charged on the
no, it's in this way it doesn't. Z2 symmetry in this way it's not broken because it's a combination of 2 objects. One is fermionic, one is bosonic, and it's like a sum or difference, whatever. So I'm not sure how it's related, right?
I need to understand more, but but okay. So I don't know. So one tempting thing to say is that, so again, in this theory, so if you look at the twisted sector, which you mean the king sector, there are states which are bosonic, which has integer spin, and there are states which are fermionic, which also has
right, but the king doesn't
so it's a mixture
have,
of them.
No, right, there's a mixture, but it's not like fermionic state and bosonic state. There is no supersymmetry in this sense. It is one state, which is neither fermionic nor bosonic.
I see.
And there is another, sector which is independent, where it would be not sum of states, but say difference of state. And it's associated with the boundary terms, effectively, if you. Okay.
I see. Yeah. Okay.
Yeah. Right.
But you can.
No, but you can imagine it's about, we do not see it. Okay.
Yeah, maybe a clarification. Sorry, never mind. For this 8 Karaman-Rana fermion, the triality is generated by gauge the Z2 fermion parity. Is that right?
Chirality.
The triality.
Oh, triality. Yes. Sorry. So triality is not generated by Z2 fermion parity. I think the triality is generated by this bosonization map, which.
You gauge the fermion parity, right?
Yeah.
But I thought that like in normal 8 Majorana with not non-chiral 8 Majorana fermion, you also have a triality. Is that right?
I think so. It's in Schuchen's paper.
Right. But that is gauge Z2 times Z2 fermion parity and another Z2.
Yeah, I don't remember.
Yeah, I have a question maybe relevant to the string theory worksheet. If I think of this kind of setup as the hydraulic string, what you told me is very similar to the Euro statement. People say that if you want to see the space-time theory's property, you need to look at your worksheet theory. If it's bosonic after GSO, your space-time theory is supersymmetric.
Okay.
If after the GSO projection, your worksheet theory it still have some Majorana fermion, your theory will be not Tachyon free. But there is an intermediate step. You can do the GSO projection. Afterwards, you still have some Majorana fermion on your worksheet.
Right.
In that case, your space-time theory without supersymmetry, but it is Tachyon free. And we indeed have Tachyon free hydraulic string theory. Like there's only one, but I mean so far we know one. I'm thinking, is this has something to do with what you did here? Is just exactly the same matching here, or is just?
I think, as you just explained, that this is give you the intermediate step. That if you do this sum of the fermion parity, namely doing the GSO projection, you still get a fermionic worksheet theory.
So the Euro statement, say that the GSO projection is the same as summing over spring structure, or is the same as gauging -1 to the F. I should more precisely understand is the GSO projection is just gauging the -1 to the F instead of really summing over the structure. Is this how I should precisely map these two things?
I don't want to make a claim in this topic.
Can I have a quick comment on that question? So in type 2 superstring, first of all, the answer depends on whether you work in Lycon quantization or BRST quantization. If you work in Lycon quantization, when you do GSO projection, the genus 1 amplitude for type 2 string is 0. And that is actually that's the Aspin structure partition function of the fermionic theory that Yunqin has. That's the only modular invariant partition function. So in Lycon quantization, you shouldn't view it as a bosonic theory. Rather, it's the Aspin structure partition function of a fermionic theory. But in BRST, you have additional non-unitary ghost, and then the story becomes different.
Okay, if there are no more questions, we can thank Yunqin again.